Hi, Jeff here with the Nurture Nature Center, and this is Science at Home. As you can see from the decorations behind me and the ugly sweater I'm wearing and my Santa hat, it's almost Christmas. In this week's video, I will show you a few ways that you can add a little science to your celebration as we talk about the science of toys. When I was young, I remember getting telescopes and microscopes and chemistry sets, but there are actually some toys that are not necessarily made to be educational, and yet they are. A wonderful example of what I'm talking about here would be a toy like this, a gyroscope. A gyroscope is similar to a top. It's something that spins very quickly. But unlike a top, it has a frame around it that allows you to hold the gyroscope even while it's spinning. And you can get these spinning very fast by pulling on a string. And as I move it around, I'm noticing something very strange. A kind of force. When I try to twist it, it feels almost like it's fighting back, like it doesn't want to move. It reminds me of the force that you feel when you put two magnets near each other, two magnets with the same polarity, and they oppose each other. I'm feeling a similar kind of invisible force, but it has nothing to do with magnetism and everything to do with inertia, or the tendency of objects to resist a change in motion. The gyroscope has some inertia even when it's not moving, but when it is moving, when it's spinning, it has much more inertia, and that gives it some stability. And that stability allows it to do some very impressive balancing acts. So for example, I can put it on the end of my finger here. It just stays there. It doesn't fall. I'm not even trying to keep it stable. I can move my finger around. The gyroscope is keeping itself upright. And it can do some other very impressive balancing. Seem to just float in midair. Another really cool toy that will teach you a lot about science is the drinking bird. So here's our drinking bird set up. You'll notice that liquid in the bottom there, and that liquid's going to make the bottom of the bird bottom heavy, right? So if I tip it over, because it's bottom heavy, it just swings back. And it swings back and forth for a little while, but pretty quickly it slows down due to friction with the air and friction with the stand here. That's probably what you expected. Unless we added some energy to, pushed it and kept it going, it should stop swinging. And it dipped itself over. Now it's swinging back and forth, and you'll notice a colorful liquid in the top here. Let's get the other one out of the way. That's rising up. Look, see that blue liquid? It's rising up into the top bulb there. Now this one started out bottom heavy, just like the other one did, but as that fluid goes up into the top, it's going to make it top heavy, which will make it tip over, take a little drink, and then it's bottom heavy again now. That fluid ran to the bottom, and it's swinging back and forth now. But very quickly, that blue liquid starts rising back up again, and it keeps going. Now, it all depends on that liquid in there. That blue liquid is methylene chloride. And methylene chloride has a very low boiling point, much lower than the boiling point of, say, water. And it condenses at a relatively low temperature, too. The air temperature in this room is warm enough that that liquid is evaporating very rapidly. And it's cooling off in the top bulb because the top bulb is colder than the bottom bulb. And as it condenses, it creates a region of low pressure that pulls the liquid up into the top bulb. And that's what makes it top heavy. The top bulb is covered in felt, and every time it dips into the water, that felt gets wet, it stays wet, and as the water on that felt evaporates, it cools off the top bulb. In the same way that our bodies sweat to keep us cool, as the water evaporates from this bulb, it keeps cool as well, and that maintains the temperature difference that keeps this thing in motion. Fundamentally, this thing works the same way that an engine works. A car engine or a diesel engine or a steam engine or even a jet engine, they all operate on the same principle. They use temperature differences to do work. The Slinky is another very simple toy, classic toy, that although it's simple, it can do remarkable things. So the Slinky is a spring. It's a special kind of spring. It's one that collapses when pushed together, but it becomes very elastic when pulled apart. One of the things you can do with a Slinky is see the difference between longitudinal waves, also known as compression waves, and transverse waves. Sound is a longitudinal wave, it's a compression wave. And we can demonstrate how it moves with our Slinky by just taking a section of the Slinky and squeezing it down. I'm compressing a section of the Slinky. And then when I let it go, you should see a wave of compression traveling down the Slinky. Let's see that in slow motion. For transverse waves, the Slinky will actually move perpendicular to the direction that the wave is traveling. Now, let me show what I mean. I'll give this a little wiggle, and that will be more like a transverse wave. Let's see that one in slow motion as well. We can use these principles not only to understand sound and waves on the ocean, but we can even use them to understand earthquakes. Earthquakes have compression waves in the field of seismology. They're known as P waves, and they have transverse waves in the field of seismology. They're known as S waves. We can also use our Slinky to learn about motion and inertia. Being a giant spring, it falls very differently from other objects. If I take this piece of wood, for example, and I drop it, the moment I let it go, the entire piece of wood begins to fall all at the same time. The Slinky drops very differently. If I extend the Slinky, the bottom of the Slinky is being held up by tension in this spring, in the rest of the Slinky. If I let go of the top of the Slinky, tension is still holding up the bottom of the Slinky. The bottom of the Slinky won't begin to fall until the rest of the spring has compressed down on top of it. There's one more toy I want to talk to you about that you've probably heard of called Kinetic Sand. So Kinetic Sand is very simple, like some of the other toys we looked at. It's just sand that's been coated in a non-toxic silicone-based oil. And this oil makes the sand stick to itself. It makes it have greater adhesion, self-adhesion. So what exactly is it? The longer you play with it, you get to the point where you're not even sure what state of matter it's in. Is it a solid or is it a liquid? Well, you know, if I take this knife here, I can cut right into this, right? And it has a very sharp edge that I can cut out of it, right? So that seems to make it seem like it's a solid. And yet if I hold it in my hands, it seems to drip down like a liquid. Well, it's neither a solid or a liquid. Rather, it's a non-Newtonian liquid. So like other non-Newtonian fluids, it acts like a liquid when very little force is applied to it. If I build a tower out of it, it starts to slump over and collapse, and it behaves like a liquid. But if you apply a large amount of force to it, it seems to become a solid temporarily. We're back in the kitchen where I filmed my first Science at Home video. And I've turned it into a little Santa's workshop here, where we're doing our at-home activity, which is making Christmas ornaments using chromatography. Paper chromatography is a method used in chemistry for identifying a liquid substance by separating it into its components, by putting it onto some paper and then adding a solvent, something that makes it dissolve. So if we're using something that will dissolve in water, you put the substance on the paper, you add some water, and as the water causes the substance to spread out on the paper, it separates out into different parts because different chemicals move through the paper at different speeds. And if we use markers and we use coffee filters, we can do chromatography to make beautiful patterns. So I found some colors that worked out really well. Then I started testing using different patterns, putting series of dots, putting spirals, circles on the paper before adding the water, and I got some really interesting results. So once you have some patterns that you think look nice, go ahead and cut them out, maybe into a circle shape, but they don't have to be a circle if you don't want them to be. Put a ribbon on them and you can hang them on your tree. From me and everyone at the Nurture Nature Center, I'd like to wish you a very happy holiday and a Merry Christmas and a Happy New Year, and I'll see you next time. Bye.